can hit recording. Okay, good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's title is Building a Trustworthy Cyber World for a Sustainable Physical World. The speaker is Dr. Guang Wang from Florida State University. Dr. Wang is an assistant professor in the Department of Computer Science at FSU. He was a Connection Science Fellow and Postdoctoral Research Associate at MIT and obtained his Ph.D. in Computer Science from Rutgers University. Dr. Guang is interested in finding meaningful patterns from large-scale data and then designing socially informed decision-making algorithms to address real-world societal challenges. Currently, his research is mainly focusing on CPS, Spatiotemporal Data Mining, human-centered computing, and trustworthy machine learning that includes fairness, privacy, and transparency, especially for applications on human mobility, smart and connected community, healthcare, economy, climate change, and sustainability. He has been publishing extensively in top-tier journals, including 65 papers in Nature Cities, KDD, MobiCom, UbiComp, VLDB, RTSS, ICDE, and WWW. He has been honored with Outstanding Paper Award in the IEEE RTSS 2021. Dr. Wang, it's a great pleasure and honor to have you as part of the webinar series at UND. Thank you so much for spending your time this morning with us, and the floor is yours for you to start the webinar.
Yeah, thank you, Prakash, for your invitation and introduction. Let me share my screen. Okay, I guess you can see my screen, right? Okay.
Yes.
Good morning, everyone. My name is Guang Wang. I'm currently an assistant professor in computer science at Florida State University. Today, it's my great honor to introduce my research building a trustworthy cyber world for a sustainable physical world. So basically, my research is mainly focusing on the cyber physical system, the CPS, which is the technical integration of a cyber world and the physical world through sensing, computation, and control. So first, massive data will be collected from the physical world by different sensing techniques. And then this data will be processed in the cyber world through different techniques like generation, prediction, and decision-making to obtain relevant knowledge. And then this knowledge will be used to control and improve the system in the physical world. So this is basically about the cyber physical system. And my research vision is to build a trustworthy cyber world by considering different factors like fairness, safety, robustness, privacy to benefit different stakeholders in the physical world towards social, economic, and environmental sustainability. For example, we are trying to improve the mobility fairness of users, profit fairness of workers, and lower the cost and improve the efficiency of operators and reduce air pollution and strengthen infrastructure of society. So within this research vision in recent years, we have been mainly focused on three research directions: the generative artificial intelligence, spatial temporal data mining, and real-time decision-making. So specifically, we have addressed the scientific and societal challenges related to different physical domains, such as mobility, delivery, and emergency with large-scale sensing data. For example, for the mobility domain, we have been working on the trajectory data generated by over 500,000 heterogeneous vehicles and over 20 million mobile devices for mobility data generation, human mobility prediction, and electric vehicle charging recommendation. And for the delivery domain, we have been working on the last mile delivery and instant food delivery with accounting data and trajectory data of over 2 million workers for the community roadmap generation and order dispatching. And for the emergency domain, we have been studying the disaster response and safe control of autonomous driving. And my technical contributions have led to over 65 publications, and most of them are published in the premium venues such as Nature Cities, KDD, MobiCom, UbiComp, AAAI. And basically, my research advanced the existing work on the three topics by seamlessly integrating cyber world and the physical world, with emphasizing utilizing cyber world's trustworthiness to power a sustainable physical world. Specifically, for the generative AI, we emphasize scalability and privacy issues. And for the spatial-temporal data mining, we focus not only on the prediction accuracy, but also for the prediction reliability. And for the real-time decision-making, we focus on the fairness and safety consideration of different services. And in today's talk, I will introduce two of our most recent work about large-scale community load network generation and uncertainty quantification of spatial temporal prediction models. So let's go into our first work about the community load network generation. So for this project, our focus problem is to cost efficiently and automatically generate community load networks on a large scale with generative AI. And our focus scenario is a community load network, typically in closed areas such as residential areas, industry parks, which is different from outdoor and indoor scenarios. Actually, this project is motivated by my real experience. So actually, one day when I tried to visit my friend, he's lived in a community built a few months ago, but I cannot find his apartment on the Google map. So I realized that the load network of many communities may be missing on the commercial maps. And in addition, community load network is become more and more important due to the ever-increasing door-to-door services that rely on the navigation, such as on-demand food delivery, last-mile delivery, autonomous driving, and emergency medical devices. For example, without community load networks, it is a challenge for the food delivery company to estimate the expected delivery time, and it also poses challenges for the couriers to find the right way and deliver the food in time. So for these time-sensitive services, such as food delivery and emergency medical services, delayed services may cause bad user experience, low business efficiency, or even loss of life. And in recent years, we saw that the load network generation has attracted much interest from both industry and academia. And different approaches are being proposed for load network generation. For example, a representative method adopted by the industry companies like Google is to employ different professional teams and devices combining with other methods like area images and crowdsourcing to collect these community load networks and remote load networks. Even those methods is accurate and reliable, it is very expensive and time-consuming. So which means that it is hard to efficiently update this map in time with low cost. And in academia, different approaches are being proposed to generate load networks, and they can be mainly classified into three categories: the commercial vehicle trajectory-based methods, area image-based methods, and crowdsourcing-based methods. Or they can combine several methods together for the load network generation. And for the vehicle trajectory-based methods, the advantages are high updating frequency and high penetration. But commercial vehicles like taxis and buses usually operate on the public open roads and rarely access communities. And in addition, the community roads have complex shapes like circular and straight and narrow wides, combined with GPS inaccuracy due to tall buildings and trees in these communities. So this poses significant challenge to generate community load networks based on the vehicle trajectories. And for the second method, for the area image-based methods, even though they can have large-scale coverage with low cost, because we can get from some open source these kind of images, they did not update frequently. And in addition, loads in communities can be covered by trees or buildings, as I mentioned previously, and severely limiting the effectiveness of image-based methods in the community settings. And there are also some other works focusing on low-cost methods like crowdsourcing due to the high cost of other methods. But it usually have uneven data quality and coverage rates. So hence, we argue that existing methods are inefficient for the effective community load network generation. And fortunately, recent years, we saw there is an emerging door-to-door services with ubiquitous digital devices provided by us a very good opportunity for the community load network generation. So, and in these services, different workers frequently travel through community load networks to deliver packages, which helped us to collect much more, rich multimodal sensing data. For example, the GPS data and magnetic field sensor data and cellular data and other sensor data during the delivery process by carrying the personal digital assistants. So this is a digital device similar to our smartphone, and they can use to collect some information. And since couriers will frequently deliver packages with high community penetration rates, because they will go to all the community to deliver these kind of packages or mails, they will continuously collect massive sensing data, which has the potential to help us to generate highly accurate community load networks at a very large scale, like a city scale or nationwide. However, we also saw some challenges using this kind of data. Actually, based on our data analysis, we found there are three major challenges to utilize the multimodal sensing data for the community load network generation. The first one is a highly uncertain courier status. So unlike the vehicle trajectory on the urban roads, delivery couriers' trajectory are more complex and uncertain, which include a mixture of indoor activities such as package delivery and outdoor delivery like walking and driving. And also for the couriers frequently switch between the indoor and outdoor status during the delivery process. So such uncertainty makes it difficult to distinguish trajectories on the load networks, while indoor trajectories might bring negative effects to the load network generation due to the GPS measurement errors. Therefore, how to detect the courier status and filter out this kind of unnecessary trajectory is important but a challenge task. And the second challenge is that the low data quality caused by the inaccurate sensing. So due to the hardware limitations and environmental effects like the high buildings and trees in the urban in these kind of communities, the GPS trajectory recorded from the device carried by the couriers may contain uncertain measurement errors. So ranging from a few meters to 100 meters. So in the complex, this kind of community environment. So as we can see from this figure, so we found more than 50% of the points have a measurement error larger than 5.4 meters. So such huge errors cause the GPS measurement cannot capture accurate geometries of the community load networks. And the third challenge is about unbalanced sensing, so unbalanced coverage. So even though there is a high penetration rate in the community, because for the courier, they will go to all the communities, but different load segments within the community are visited with different frequencies. So some loads are frequent or with high frequency, and some others are barely visited. So which brought uneven GPS coverage rates on different load segments. So this also caused a challenge for the accurate community load network generation. So combining these three challenges makes the load network generation based on the multimodal sensing data a challenge task. And to address these challenges and to generate the community load networks. So in this work, we designed a novel framework called Small Map. So which leverages ubiquitous multimodal sensing data from last mile delivery to automatically generate high accuracy community load networks with low cost. Basically, our small map consists of two key modules. The first one is a trajectory of interest detection module, so which is utilized to remove the noises from the trajectories based on the courier status detection to address the first challenge we mentioned about the uncertain courier status. And the second module is a community load network generation module. And this is based on a new technical design, which is called dual spatial temporal generative adversarial network. And particularly, we have two designs in the network, which include a load GAN and line GAN. So particularly, a load GAN is developed to generate the load networks from the aggregated trajectories that address a second challenge, and about the accurate sensing. And a line GAN is designed to impute the generated load structure with low visitation frequencies and address challenge 3 about unbalanced sensing. And next, I will introduce a key design of the two key modules. So as I mentioned previously, the first module is about the trajectory of interest detection, which is utilized to remove the noise from trajectories. And the motivation about this design is that we need to detect the indoor and outdoor status of the workers or the couriers. So the motivation of this trajectory of interest detection is to filter out the noise or non-relevant information from the multimodal sensing data, including the indoor trajectory, outdoor trajectory, and staying points. Intuitively, we can easily segment indoor and outdoor trajectory utilizing spatial boundary of the buildings. However, we found it is not feasible in a real-world setting because indoor trajectories have large deviation errors and thereby often shift out of the building boundaries. And actually, based on our data analysis, we found that the PDAs, the devices carried by the couriers, offered us a good opportunity to overcome the challenge of indoor-outdoor status detection by utilizing the sensors embedded in these devices. Our intuition is that the indoor and outdoor environment have different impacts on the sensors reading. And in this work, we designed a lightweight multi-sensor fusion algorithm by modeling these sensor values to detect the indoor and outdoor status. However, we found that only using the sensor data is inefficient in our scenario, since the sensor readings are influenced by environmental factors like the buildings and the trees I mentioned, that we also designed a voting-based approach to enhance the detection performance. So in particular, we run the detection algorithm every second. So we will get 10 detection results between two GPS points because the GPS sample rate is 10 seconds per point. So if the detection sequence for a GPS point indicates more indoor status than outdoor, the point is classified as the indoor point. So actually, we deploy this lightweight algorithm on the PDA devices carried by the couriers, which only send detection result to the server instead of the raw sensing data, because the data transition will cause a huge energy cost, which is not applicable at a large scale. And similarly, we also need to remove the out community trajectories. However, the out community trajectories may also shift it to in community, and we need to remove them. So for example, the point 1, the P1, P2, and P3 in this figure. And to address this challenge, our intuition is that shifting points have prior and subsequent points that are outside of the community in a given time window. So we detect such shifting points to get in community trajectories by computing each point preceding and succeeding points. And in addition, in communities, couriers sometimes stay at the location to take a break or contact the customers, not on the load segments. During these stay events or stays, the GPS signals can shift away from the two locations and cannot reflect the load networks. leading to the considerable deviation errors. Hence, we detect state points based on the location and timestamp information. Our intuition is that if a trajectory segment stay within a certain meters for more than a certain minutes, the segment is classified as a stay point. And the parameter can be adjusted according to different environments and settings. So such as a small the distance and small in area with a minimal GPS shifting. So based on our observation from the real world data, we set R as 20 and M as 2 in our experiment. And after we detect the current status, we can obtain the trajectory of interest by removing the indoor and out community and state trajectories from the raw data. And after we get the trajectory of interest, the next step is to generate load networks from the trajectory of interest, which means that we get the noisy trajectory and we use this as an input to generate the load networks. And in this work, we design a dual spatial temporal generative adversarial network to achieve this goal. The reason to adopt the GAN-based model is that it has been empirically shown to be able to reconstruct accurate topology information from the sensing signals. And however, there are still some challenge to use the GAN-based model to achieve the generation tasks. And the first challenge is about the data format incompatible issue. As we know that the trajectories are spatial temporal data that contain timestamp information, which is different from load networks. And these data format incompatible issues pose a challenge to existing GAN-based model, making it impractical to directly use the trajectory as a GAN model input. And in this work, to address this challenge, we designed a mapping mechanism to project low trajectory and the load network into the same domain for the GAN training and inference. And for a collection of trajectory of interest in a community, we map all trajectory points into a two-dimensional matrix by normalizing trajectories using the community spatial boundary. So here, the latitude max, latitude minimal, and longitude max, longitude maximal are the minimal and max latitude and longitude of the community, and D1 and D2 are the dimensions of the matrix. And the second challenge is lacking of the training data. As we know that training a deep learning model, a GAN-based model, require large-scale data. However, it's a challenge for us to collect the large ground truth loads and noisy training trajectories on the corresponding nodes. So to address this issue in this work, we designed a data augmentation method by area of interest boundary. So intuitively, a load network partitions a region into different areas by load passes. So which is similar to the area of interest boundaries that partition an area into different area of interest. Therefore, we may use existing area of interest boundary data, which can be collected on the platform, such as the open source map, like OpenStreetMap. However, the main load network is very different from community loads, which means that the shape is very different. Therefore, we combine the area of interest boundaries and the main load network skeletons by expanding the AOI boundaries until they connect with loads to obtain synthetic loads, so which are similar to the community loads. In this way, we can get a synthetic load network in different shapes. And since the real GPS points alongside the load network follows a mixture Gaussian distribution, we add the noise to the AOI partition image by sampling synthetic GPS points from multiple Gaussian distributions. However, the load network structure in this figure B is too clear and easy to recognize, so which does not benefit the generative model, and it cannot provide a realistic training environment that I presented previously, that the real world scenario, there are some load segments are covered by many GPS points, but many load segments don't have any GPS points. So in this case, to address the issue, so we further conduct two-step load network adaptation to replace the load segment with sparse noisy points to make it similar to the real trajectory. As we can see from the figure C, the load network adaptation. So we get the training data X, and also we have the AOI partition boundary as our training label Y here. So after we get the training data, we can train our generative model load GAN to generate the load networks from the noisy trajectories. So the training objective consists of two parts. The first part is a loss from the conditional GAN, which is called CGAN, and the loss from the L1 loss, because the conditional generation typically generates samples from source domain data samples, and L1 loss captures the low-level features such as boundary and shape information, which is important for the load line generation. And the generator is based on the encoder-decoder architecture, and the discriminator is based on a convolutional neural network. However, one of the major challenges for the generative model to generate the image with strong topology structure is a dead-end effect, which means that the generated lines or curves are suddenly broken and impact the generation performance. And to address this issue in this work, we further designed a line GAN to impute these broken loads. So the input of the line GAN is the output of load GAN, of the load GAN, as we obtained from our previous step. Since it is also challenging for us to train the load GAN, the line GAN due to the lack of training data, so we further design a data augmentation approach. So this is similar as we did for the load GAN design. So to simulate the results with the dead ends generated by the load GAN, we further sample n grids in the area of interest boundaries and remove the loads in the selected grids. Thus, we turn a connected AOI boundary into a load network that is similar to the load networks generated by the load GAN. So, which means that we get the similar load network with dead ends. And after training with the constructed data, the line GAN can generate more accurate load networks based on the output of the load GAN. So in this case, we have the load GAN and line GAN. The load GAN to generate the load lines, and the line GAN to impute the dead ends of the output of the load GAN. So to evaluate our small map, we utilize a multimodal sensing data set collected from over 100 communities by around 200 couriers during their delivery process from 2022 July to August, including over 11,000 trajectories and over 3 million GPS points. And we utilize the AOI partition polygons to construct over 4,000 trajectory load network pairs to train the load network generation models. We adopted several widely used metrics, including the load difference rate and precision, recall, and F1 to evaluate the model performance. And we also compare our framework small map with other state-of-the-art baseline models from MobiCom, UbiComp, ICDE, CVPR. And as we mentioned, that one challenge in this project is to collect the ground truth data, because even though we can use our generative AI model to generate this kind of load networks, but we need to collect the ground truth load networks. And for the courier status ground truth generation collection, we develop an app that run our indoor-outdoor recognition approach. As I mentioned, we embedded this on the PDA devices. And for the community load network ground truth collection, we manually weighted the communities with high accuracy localization devices, equipped with an RTK localization modules and GNSS localization module. So this is a very high accurate sensing devices that can capture a very accurate these kind of locations. And the reason why we cannot use this kind of method for large scale deployment, because the high accuracy localization device is very extensive and has high power consumption, and is also labor intensive. As we know that we need to cover all the load segments to collect the ground truth data when we try to do this project. Actually, we traveled. We went through I think almost 100 communities to collect the ground truth data by our designed devices to get the to sense the load segments. And then after we get ground truth data and our generated data, and then we will do both qualitative and quantitative evaluation. And we show both quantitative and qualitative results. From this figure, we can see that our small map generates loads most similar to the ground truth nodes in terms of overall topology and geometry. And we also show the imputation effect of our line GAN. It can be noted that the load network with multiple dead ends can be imputed by our line GAN, so which is very similar to the ground truth load network here. And we also show the quantitative comparison between our small map and baseline models in two cities, Beijing and Chengdu. And we can see our model achieve the better performance among the four metrics. We also compared the computational efficiency of our model and the existing models. We found that the training process of our model is very efficient, so which takes less than 2 hours to generate a city of a size 50 kilometers times 50 kilometers. And so actually our small map has been successfully deployed in the Jingdong Logistics, which is one of the largest logistic companies in the world, which is utilized to improve the delivery efficiency based on different downstream use cases. So the first, we first utilize our small map to help for the travel time estimation, and we found that the mean error rate of travel time estimation with small map is 0.092, which is 0.555 if we do not use our small map. And another case is to utilize to estimate the courier workload. So we utilize the courier's calorie consumption to quantify the workload and show the workload estimation with or without community load network generated by our small map. And we found the estimation error significantly decreases with our small map, which we showed that with our small map, we can accurately estimate the courier workload for other tasks like order assignment or other tasks. And to summarize, in this work, we designed a scalable community load network generation framework, which is called small map, which efficiently generates community load networks from multimodal sensing data collected by couriers during the delivery process. And a trajectory of interest detection module is designed to filter out irrelevant trajectories such as indoor trajectories, out community trajectories, and a dual spatiotemporal GAN model is designed to generate the load networks, combining a load network generation module and a line GAN to accurately generate the community load networks. And to obtain enough data for the training of the two GAN models, a data augmentation approach is proposed to generate synthetic training data from the area of interest data. And we implement and evaluate our small map with data from over 100 community collected by over around 200 couriers. The evaluation results show our small map can achieve about 91% of precision, recall, and F1 score. And it has been deployed on one of the largest logistic companies for the downstream applications. And also our small map can be potentially applied to other services such as unmanned urban delivery and autonomous driving. It can also help commercial maps updating, for example, the Google or other commercial maps. So here I have introduced our first project. I'd like to know whether there are any questions here, or I can move forward for our second project. Okay, maybe I can continue to our second project, and then I will answer all the questions. So our second project is about the reliable prediction. So we will introduce another very interesting topic, which is called uncertainty quantification. So which utilizes for the robust and reliable spatial temporal prediction tasks. And and the reason why we focus on the spatial temporal prediction is that it is important for many real-world applications, such as crime prediction, crash prediction, and mobility demand, climate change, and autonomous driving. So this is a very important direction for the spatial temporal domain. And the background of this work is that we saw that spatial temporal prediction models transitioned from the traditional numerical outputs to considering potential variations in recent years. So like in this figure, when we predict the number of crimes in each region, previous deterministic prediction only outputs the numerical values, but the probabilistic prediction also considers the prediction uncertainty, such as prediction intervals. So here, a new question is that how to measure the predicted uncertainty is good or not? So this is a question we need to answer when we try to quantify the uncertainty of our prediction. And so uncertainty calibration is a potential way to answer this. So actually, uncertainty calibration is a post hoc uncertainty quantification method. The intuition is that to align the predicted probability of a model with the actual empirical frequencies of the outcomes, which is important to provide reliable prediction for the risk involved tasks, such as the safety management, autonomous driving, healthcare, and other finance domains. So let's give a concrete example about the uncertainty calibration. So as we can see from this figure, if we ask, are you going to take an umbrella given the following probability of raining? So as we say that the probability of raining in the morning 7 a.m. is only 5%. So if the weather forecasting model is well calibrated, it may not worthwhile to bring an umbrella, since the probability of raining is only 5% at 7 a.m., right? So from a frequentist perspective, so if the weather condition at 7 a.m. can be observed repeatedly over a large number of random chance, only 5% of them are going to rain, right? So however, if the uncertainty are year calibrated, it is likely that 40% of those random chance at 7 a.m. will end up raining, right? So if it is not well calibrated, the probability may be 40 or 50, right? So in this project, our focused problem is to design a general uncertainty calibration framework that can be adapted to improve any existing spatial prediction models. Actually, we are not trying to design some new a spatial temporal prediction model because there are already a lot of these kind of models. So we are trying to calibrate their uncertainty of these models. So, however, we found there are two major challenges to tackle this problem, especially for the spatial temporal prediction domain. The first one is sparsity and asymmetrically distributed nature of the high-resolution spatial temporal data. So actually, sparsity issue is ubiquitous in the spatial temporal domain. When we increase the spatial or temporal resolution or granularities, right? As we can see from this figure, so when the prime data transitions from the coarse-grained to the fine-grained, the probability density of the data shifts from the symmetric and dense Gaussian distribution to the asymmetric and the sparse negative binomial one with a significant increase number of zeros. There will be a lot of zeros if we have a high resolution spatial temporal data. And in addition, the sparse data usually divide from the model's mean variance assumption. So existing variance-based metrics not fit to our problem, right? So to address this challenge, in this work, we designed a sparsity-aware uncertainty calibration framework, which includes a post-hoc uncertainty calibration method to calibrate the outcome from any spatial temporal prediction models to align with the true sparse data distribution. So this shows a typical spatial temporal prediction framework. So let's use the spatial temporal graph neural network as a concrete example. So typically, a deterministic spatial temporal graph neural network models tries to learn a function f. Tries to learn a function f here to predict the target value of the future, to utilize the input data from previous t time step to predict the target values of the future, maybe k step or m steps. It usually includes two key components: a spatial temporal embedding module, which is utilized to extract patterns from the input data, and a prediction module, which is utilized to learn numerical prediction values of the future time step. So we usually use a full connected layer for the prediction module. So since we are focused on the prediction uncertainty, we modify the existing spatial temporal prediction models into the probabilistic prediction models that can utilize to predict the distribution of each future data points without revising the spatial temporal embedding modules. So in this case, we do not revise the spatial temporal embedding modules, but we will revise the prediction models. So specifically, we modify the prediction layer to infer the parameter mu and alpha of the negative binomial distribution to accommodate the sparse data in this study. And M, H, and A, M, and H here are the set of predicted mu and alpha. Then we feed this prediction result to a post-hoc prediction interval calibration module. So we designed a new prediction interval module. So when we will evaluate our calibration results through different methods to get the calibrated model. So next, I will introduce our key design about the prediction interval calibration. So different from traditional calibration methods that usually calibrate variance by assuming Gaussian distribution, in this work, we focus on the prediction interval calibration because it is more suitable for the negative binomial distribution of sparse and symmetrical data. And first, we construct the distribution prediction interval of the negative binomial as I, and our target is to ensure the prediction module F to be calibrated. Basically, it shows that we want to ensure 5% percentile of prediction interval should really cover 5% of data, and 50% percentile covers 50% of data. So formally, it can be expressed in this formula, right? And then in this work, we adopt the quantile regression to calibrate the prediction interval because it predicts specific quantile and can manage this data set with variance fluctuation in sparse data. And given M and Y from the calibration set, quantile regression Q models Q equal to M beta, which fits the different quantiles of the data. So inspired by the zero inflated models, we set up two quantile regressions on the zero and the non-zero prediction separately, which depends on the value of M. So for each part, we fit the 5% of a quantile and 95% of quantile of the data to ensure a reliable prediction interval. And the collaborative model is then applied to predict the model output on the testing data set. And after we introduce our design, we also evaluate our SAUC using two public data sets. So the first data set is the Chicago crime records. So which is sourced from 77 census tracts from 2003 to 2023, covered 20 years. And another data set is Chicago traffic crash data, so which is sourced from 277 police beats between 2016 to 2023. So we can see that sparsity increased significantly in the dataset when scaling up the spatial resolution. For example, from 1 day to 1 hour, right? And in this work, we utilize 60% of the data for the training, 20% for the validation, or we call it the calibration, and 20% for the testing. And so we utilize three most popular spatiotemporal graph neural network models. As I mentioned that we will not design new models, we just adapt existing models for base models, prediction models. And we utilize 5 uncertainty calibration models as our baselines for comparison. And in this work, we also design a new prediction interval calibration metric for the asymmetric distribution, which has not been studied before. The intuition is that a model is calibrated if data variance align with the prediction intervals. So this means that for each value of uncertainty measured by the prediction interval, it will match the predicted error. So hence, we define the expected normalized calibration error, which is ENCE. So which intuition is that CMPIW and observed RMSE should be approximately equal. The smaller the better. And in this work, we also utilize 2 other metrics to measure the performance of our model. The first one is the reliability diagram, and the second one is the risk score. And first, I show some results here. As we can see from this figure, so we saw that from the performance perspective, our SAUC reduced the ENCE by around 23% compared to the competitors, and our SAUC can effectively for the collaboration, especially when we separate the zero and the non-zero data, so which can address the zero inflation issues for the sparse spatial temporal data. And we also present the reliability diagram on the Chicago crime records dataset. And the diagonal line means the perfect calibration, which is what we want. So results closer to the diagonal line are the better. So we found our SAUC shows superior calibration performance, particularly for the zero values. And this may be due to our SAUC can handle the heteroscedasticity issue. And since uncertainty is highly related to the risk assessment and the reliability, so we adopted the risk score from the reliability research to evaluate the performance from the spatial perspective. And we define risk score equals to the anticipated risk times the prediction uncertainty. So which means that the higher risk to the predictions are characteristic by both large prediction mean values and high uncertainty. And we find that SAUC accurately pinpoints the high-risk areas, surpassing other methods in mirroring the actual instance patterns. And to summarize this work, so in this work, we designed SAUC, a generic uncertainty calibration framework that can calibrate sparse and symmetrically distributed data. And our model can be adaptive to any existing spatial temporal prediction models to measure the prediction uncertainty for reliable prediction. And in addition, we also designed a new prediction interval-based calibration metric to fit sparse and asymmetrically distributed data. And we evaluate our SAUC on 2 public datasets and compare it with 5 popular uncertainty calibration methods. And the results show our SAUC effectively reduced the calibration error by around 23% compared to other baselines. And our work indicates that prediction models should consider uncertainty for reliable predictions instead of only focusing on the accuracy. And our SAUC has the potential to generalize to other safety-related applications like transportation, finance, healthcare, where sparse and symmetrically distributed data are also very common. So I have introduced 2 of our most recent works. And let's summarize my research. So basically, my research seamlessly integrates the cyber worlds and physical worlds and aims to build a trustworthy cyber world for a sustainable physical world. So we consider different factors like fairness, privacy, and robustness, reliability. And to achieve this, I have been focused on 3 directions, including the generative artificial intelligence, spatial-temporal data mining, and real-time decision-making. So with fairness, safety, and we design innovative methodologies and perform real-world deployment and community engagement for societal impact. So actually, I have some other very interesting work, but due to the time limitation, I think that I cannot introduce all of them, but you can check them on my website. Thank you very much for all of you. Thank you very much for being here today, and now I'm happy to take any questions you may have.
Thank you so much, Dr. Guang, for your talk, and appreciate for sharing your uncertainty calibration framework with us. It's exciting and to see what you've done. So now we can take a Q&A. Maybe I'll start with the first question. I think, can you go back to the slide where you talked about sparsity? I couldn't understood the resolution of this sparsity table. Why as the resolution increases, sparsity increases? I can't remember.
You mean I think this table?
I think you had it. Yeah, this one. Yes.
This table, right? Yeah.
Yeah.
Okay. So the sparsity means that there are many zero values. So you know that when we predict, so we will first do the partition of the city. We will divide the city in different regions, right? So when we do the prediction, we will predict the value for each region. So when we are trying to predict for daily prediction, so for example, in a region, in a day, maybe there are some crime, right? But in hourly, they may have no this kind of crime. So there is a zero value in zero values here, right? So when we try to increase the granularity or resolution from 1 day to 1 hour, I think there are too many zero values in our data. So this is what we call sparsity.
Okay, the number of instances are increasing. Okay, I see that.
Yes,
okay.
Yes.
How about this? What happens to your uncertainty calibration set in this particular case? Would you have more? Do you do a lot of augmentation? In this type of training, or the more 1 hour resolutions? Are you seeing more error in terms of the accuracy. How is your accuracy, in the prediction with reference to 1 hour scale versus the 1 day scale?
Yes, I think this is a very good question. So I think that your question is that when we trying to have the calibration, also the calibration, whether the accuracy will decrease or not, right? Yeah,
Yes.
actually, I didn't show the result. Actually, we have this result in our paper, so in the appendix. So actually, we adapt our model based on existing models, right? So because we want to adapt existing deterministic models for the probabilistic prediction. So actually, you are right that normally that if we don't have any designs, maybe the accuracy will decrease. So this we found in our experiments. But based on our design, because we consider both we have a new design. We separate the data into the zero and non-zero prediction, and for different prediction tasks. And then in our design, we found that our results, even though it's lower than the existing models, but it's very close. I think that we can achieve the comparative result accuracy compared to the existing models, but we can also quantify or calibrate the uncertainty. Yeah, I think that this is a very good point. Thank you.
And another question is, have you looked at other methods other than the quantile regression? What is so unique about this quantile regression that is more deterministic in nature? I get that. Is there a reason to?
Yeah, I think that thanks for this great question. So the reason I think that this why do we consider the quantile regression, right? I think this is a very good point. I think that actually I know that there are different methods to do the uncertainty quantification. I know that you have some work on the uncertainty quantification, right? So I think that basically that for the uncertainty quantification, there are model uncertainty and data uncertainty, right? And then in this work, we are trying to build a general calibration framework that not rely on any data distribution. So we will not assume that this data will follow the Gaussian distribution or other distributions, right? So we want to find a way that can calibrate any distributions. So actually, we searched for some methods, and we found that the quantile regression can be a good method to address the prediction interval calibration. So this is the reason we select this method. But I think that you mentioned that there may be another method or other method can also use to adjust this method. I think that is also a potential direction we need to explore. Yeah, I think this is a good direction. Yeah.
Okay. Thank you. We have another question from Dr. Utku.
Okay.
He'd like to ask, what do you think about using combination of generative AI-based agents communicating inside a smart city setup? What do you think about advantages of possible issues?
Okay. Yeah. I think this is a very good question. Actually, this is also a direction we are trying to explore. I have one student who is trying to design the large language model, the LLM model agent for the urban partition. So it's basically for the urban planning or other area partition or task, this kind of allocation. So I think this is a very good direction. I saw there are some papers from the smart city area or spatiotemporal data mining area. There are already some publications. I know some professors who they are working on this, and also I have one student working on this. I think this is a promising direction. So one of our work in this area is that we are trying to design the LLM agent for the urban partition. So like in the delivery area, like the logistics area, we want to divide the area into different zones for the courier to deal with the packages, right? So we want to consider different factors like fairness, like efficiency, like other factors, right? So we are design. So actually this is our initial step. So we are designing this kind of LLM agents based on two types of data. So one type of data is from domain knowledge experts. For example, the manager who makes the decision for this kind of partition. And another data is from the order data, right? How many orders and what is the spatial temporal, this kind of context of these areas. We will fit these two data for our LLM agent design, and then use them to communicate. They will do the communication, right? The agent will communicate. I need to address this kind of region. I need to divide this region to different other regions. I need to assign this order to other regions. And then based on this, we can do other downstream tasks. I think that Professor mentioned a very good point, that utilizing the LM agent or generative AI-based agents for the smart city applications. I think this will be a very exciting direction. Yeah.
Thank you. Another question is in terms of cybersecurity, looking at privacy preserving approaches. When we look at traffic data, how do you, what is your thought on actually, these uncertain calibration set, all these models are great, and at some point these need to connect to some cost function optimization.
Yes.
Still, arrive at some optimal solution that's still cost effective, scalable, at the same time, somewhat you address some privacy. Have you, as your group is looking into any kind of aspect into that?
Yeah, I have one student who is working on the privacy preserving data generation. I think it may be not maybe a little different from your question here, but I can introduce this work. So actually this project is just funded by NSF. It's funded by CSSI, the cyber infrastructure. So it's a big grant. It's 2.3 million project. So it's led by my Ph.D. advisor. I'm the site PI of FSU. So actually, for this project, we are trying to, because that there are a lot of privacy issues, right? So for the smart city or spatial temporal data, right? So, however, as we know that it becomes more and more challenging for us to access this kind of data. So the motivation of our project is that we are trying to generate the synthetic data based on the general AI. And we are trying to publish this kind of data for the to benefit society. And also another motivation is that nowadays when we try to publish a paper, right? So we need to publish our data set and the models. So if you didn't publish your data set or models, maybe do not publish data set, maybe fine. But some reviewers may argue this, right? So when you're trying to release your data, but this data are very sensitive, what should we do, right? So what we want to do is that we were trying to design a cyber infrastructure that you can fit your data into our cyber infrastructure and generate some synthetic data. And then when you're trying to publish your paper, you can publish this kind of synthetic data alongside your paper. I think this is a direction about the privacy we are trying to solve. But I think that Dr. Prakash, you mentioned that for this kind of model, this kind of privacy or security, right? So this part, like the loss function or other model attack, actually we do not. I think that we have our collaborator. They work on the privacy. We just published a paper in KDD this year. We are trying to attack all the point of interest recommendation models. So this is something we have been done. But from my side, I'm more focusing on the data part, the data synthetic and the generation.
Yeah, I think we're good with reference to the questions. I want to share one thing. We have an upcoming conference coming up at UND. And do you see the screen?
Yes, I can see the screen.
It's an IEEE fourth cyber awareness and research. So AI and cybersecurity paper. So I would encourage you to submit a paper. We have the deadline is end of July. So I appreciate if you can spread the word and help me in review process and also submit some papers. That would be great.
Yeah, it's my pleasure. Yeah, it's my pleasure.
But thank you so much for your time this morning. I think it's nice to get to know your group and what you work, and maybe possibly we'll find a ways to collaborate with your team.
Definitely.
And thank you so much for your time this morning.
Yeah, thank you for the invitation. Yeah. Thank you.
Yeah, take care. We'll be in touch.
Take care. Yeah. See you.